evening, everyone. My name is Vicky Calogera. I'm the director of CIERA, and I'm happy to welcome you to this virtual event about our home galaxy, the Milky Way. Thank you so much for tuning in tonight. Let me first start by telling you briefly about CIERA. We are a research center at Northwestern University, one of about 50 research centers. Universities are generally organized into schools and departments, but there are also centers like ours that span across the entire university. This creates collaboration across departments, and we collaborate and connect astronomy to other fields of study like engineering, computer science, statistics, and applied math, even to areas like journalism, education, and information technology. That's what the interdisciplinary part of our name means. CIERA stands for the Center for Interdisciplinary Exploration and Research in Astrophysics. Now, let me introduce our speaker tonight, Shane Larson. It's a special pleasure for me because I've known Shane for many, many years, since he was a finishing graduate student and I was a beginning faculty member. So we go back a long way. Shane is now the Associate Director of CIERA, and he's also a Research Associate Professor at Northwestern University in the Department of Physics and Astronomy. He earned his master's and doctoral degree in physics from Montana State University. He's an award-winning teacher and a fellow of the American Physical Society. Shane's interests include gravitational waves, as well as data analysis and a variety of cosmological phenomena like binary star evolution and gravitational dynamics. Now, he has an incredible passion and gift for public communication of complex physics and astronomy topics. This means that he can talk with anyone, not just other scientists, but about what he studies in the universe, but the general public, from children all the way to older adults. In fact, inside CIERA, he very often helps us understand very challenging topics outside our own area. Shane writes a public science blog, and he's active on Twitter. Our team here will place the links of Shane's blog and Twitter into the chat box. So please click the chat button in a moment, and you will see these links and other interesting tidbits throughout the talk announced in the chat area. Now, before I turn things over to Shane, let me explain how we will take questions. Later on, after the talk, Shane will be answering questions from all of you. So if you'd like to participate, please do the following. Look at the bottom of your Zoom screen and use the Q&A button at the bottom and type your question in the window that appears. You may be more used to the chat function of Zoom, but for questions, please use the Q&A button instead. I'll be looking at the Q&A list. Our goal will be to answer as many questions as we can following the program. You can ask questions at any time, starting now. I'll be watching for your questions during Shane's presentation, and I'll read them aloud when the time comes so that Shane can answer them. Now, one more request. If you are a young person, or you are helping a young person enter a question, please tell us in the question box. We love kid questions. We'd like to take as many of them as possible, and we want to make sure we will answer them. I also want to let you know that we are recording this event, and we will post the video on our Northwestern CIERA YouTube channel, and the link for the channel will also appear in the chat window. So at this point, I'm very happy to welcome Shane. So Shane, please take it away.
Okay, thank you, Vicky, for that introduction. And thank you, everyone, for being here with us tonight. As scientists, we spend a lot of time talking among ourselves, but there's a special pleasure that I think we all gain in going out among the people who share our communities with us and talking about things that are very near and dear to our heart, which is certainly what I'm going to do tonight. I hope you're all safe and well. This Zoom format, this virtual format, is new and different, both for giving talks as well as participating in talks, but it affords special opportunities, which is people who might not normally join us are able to check in. So you'll see appearing on your screens an anonymous poll popping up right now. asking you where you are joining us from. Now, Northwestern University is in the greater Chicago area in Evanston, just north of Chicago. So we expect most people will be from the area around us, but we would like to understand where you might be joining us from, and certainly welcome you to this virtual event with us. So if you take the chance there, just click on the result and we'll let it run for a few seconds here. And when it's up, we'll see the results to where people are joining us from. So that's been maybe 30 seconds or so. So we'll close the poll and see where everyone's from. And those results will be popping up. Okay, there they are. So yeah, as expected, you see a lot of people in the central US there, where we are in Evanston. But then we do have some folks from the West Coast and farther afield in the East Coast here in the United States. So thank you all for joining us. We certainly hope you enjoy the evening. We're going to talk a little bit here for 45 minutes or 50 minutes, and then at the end, we'll take questions as Vicki described. So I'm an astronomer, and so the science that we do is related to trying to understand our place in the universe. And the things that we like to understand are far-ranging, ranging from what are the nature of planets and things that life can inhabit, to the nature of the stars and where they came from and how did they change over time. And so tonight we're going to talk about the Milky Way galaxy. And so you can see here behind me an artist's rendition of the Milky Way. This is a view of our home galaxy that no human has ever had and likely never will, because it's a view of what the Milky Way looks like from outside. It's something that we have used the tools of science to come to understand, both by studying the Milky Way itself, but also by looking at other galaxies in the universe and trying to understand how their properties might tell us something about our own home. This kind of visualization is only possible from our colleagues who are in the arts, who can take the things that we as scientists tell them and turn them into a rendition like this that you and I can understand and appreciate. So we're going to talk about the structure of the Milky Way and how we came to understand it tonight. At the end, we'll talk about some of the work that we're doing in CIERA, in my group in particular, to understand the Milky Way a little bit better. Okay, so let me go ahead and start a few slides. So there's my blog link right there. So you can certainly go to my blog and read about a lot of the different things that we do in astronomy. I talk about a lot of different things. It's meant to be for the public. As I tell people, it's for my mom, so she knows what I do. My mom is not a physicist or an astronomer. She's a forester. So hopefully it's accessible. My social media links are there as well. So this is a different artist rendition of the Milky Way, as if you were looking straight down on it from above. And it shares many of the features that you will have noticed in the first image that I showed you behind me. In particular, it has a bright central region that we call the bulge. You'll notice that region is a little bit yellow. That's because the stars there are older. And then it has these majestic, twirled up, spiraling arms. And those spiraling arms are blue, and you see reddish images here, reddish areas here in the image. Those are star-forming regions, and the disk is generally regarded to be a place where stars are born and are more young than they are in the center of the galaxy. So the sun lives in the Milky Way, not at the center and not out at the very edge, but it lives down in the disk, down in these regions of young stars, in a region called the Carina Cygnus arm. And so you can see where we marked out. And part of the story tonight revolves around coming to understand how the sun's position was determined in the Milky Way galaxy, discovering where it is in our own home galaxy that we actually live. And this is really the point in understanding the way the Milky Way came to be understood, is our understanding is always defined by the questions we can ask and then the ones that we can answer. So asking a question like, where is the sun, is an example of that. And we'll use our story tonight to examine some of those questions, okay? So for most of history, the Milky Way was really a mystery to humanity. It is seen easily if you get out away from the city lights as a diffuse gossamer band of light stretching up overhead. It looks like clouds if you're unfamiliar with it, but it is this band of light that stretches up over your head from one horizon to the other, particularly during the summer months here in the Northern Hemisphere. We call it the Milky Way because of that faint white translucent appearance, but in cultures around the world, it has other names. In the Kalahari Desert in Botswana, the Bushmen there call it the backbone of night because they believed it was actually the structure holding up the sky, okay? But knowing that it's there and seeing it provokes a very deep question, which is, what is it? It doesn't look like anything else that we see when we look around the world. It looks like clouds maybe, but it's not clouds. It doesn't move across the sky. It doesn't change structure. It's there every night in the same place. What is the Milky Way? And for 40,000 generations of humans, we didn't know what the Milky Way was because our senses aren't tuned finely enough to understand what the universe is showing us. In order to probe deeply into the secrets of the universe, we have to harness technology to allow us as humans to detect and discover things that our bodies aren't built to do. And in this case, the piece of technology that revealed what the Milky Way is was a telescope. The first telescope used for astronomical purposes was by Galileo Galilei in 1609. He was the first person to turn his telescope to the skies and discover that it allowed him to see things that his eyes could not. In a way, he transformed our understanding of the galaxy instantly. In a way, he made the galaxy into something that we never knew it was. So he did this in 1609, and in 1610, he wrote a very famous book called Sidereus Nuncius, the Starry Messenger. So it's written in Latin, and if you've ever seen one of these on display at a museum, and you can see it in museums around the world, it is written in Latin, but you can get English translations. And the part about the Milky Way, I've replicated here in English. And so I'd like to read this to you because I think it's important. The galaxy is nothing else than a congeries of innumerable stars distributed in clusters. So congeries is a word that kind of means clusters. To whatever region you direct your spyglass, your telescope, an immense number of stars immediately offer themselves to view, of which very many appear rather large and very conspicuous, but the multitude of small ones is truly unfathomable. Okay, and I've added the highlighting there because I think it's the important part about what Galileo realized almost instantly. To your naked eye, there are only 8,000 or 9,000 stars visible if you were to travel all over the world and count every star you could see. But through the telescope, he discovered there were far, far more than his eye could ever see. And this little bit I've highlighted here at the end points to the fact that he immediately realized there were more than even his telescope could see. Today, we know that the galaxy contains some 400 billion individual stars, okay? Far more than you can imagine counting, even with a telescope if you were out on a clear night, okay? So this really transformed our understanding of what this diffuse band of light was, and it immediately sparked people's attention there to direct their studies of the universe to try and understand, well, what's with all those stars that we can barely see? That diffuse band of light is the combined light of 400 billion stars that are too dim to see except with your telescope. So what can we learn about the Milky Way if we use the telescope and study the stars? So it took about 175 years or so, but in 1785, William and Caroline Herschel, who were astronomers in England, decided that they would take on the task of mapping out the Milky Way. Right? We could tell all of these stars make it up, but there are stars all over the sky. And when you look at the Milky Way, it apparently has defined edges. So what if we used our telescopes to try and map out the extent and the shape of the Milky Way? Okay, and they used a very special, interesting technique called star gauges. And I'm going to tell you what star gauges are here in just a minute because they kind of play a role in our understanding of the way we've approached the Milky Way in many different ways. But paper is a wonderful thing. And in fact, the original paper about star gauges is still available. It's been scanned, and so you can get it digitally at the Royal Society Archives. And then there's a very nice paper I've linked there at the very bottom, which has a modern explanation of what star gauges are. But let me tell you how star gauges work, and we'll use that to talk about how we discovered the shape of the Milky Way. So Herschel was an exquisite scientist. He and Carolyn both understood very well that there are limitations to our knowledge. But astronomy, unlike other sciences, it's very difficult to overcome the things that we don't know, precisely because we're confined to sit here on the Earth. Astronomy is a spectator sport. The only thing you can do is look and ask, what can you see of the universe from your place right here on the planet? You can't go out and grab spoonfuls of stuff and take it back to your laboratory and measure it with rulers and put them on scales and do experiments. All you can do is look. And so very often, the things you would like to know, you simply don't know. And so you have to make assumptions that help you understand what the boundaries of the possible nature of the universe might be. And so the thing that Herschel didn't know is what is the intrinsic brightness of every star that he sees in his telescope. So if I were to phrase this in the context of light bulbs, what he didn't know is when I look at a star, is it a 100-watt light bulb or is it a 20-watt light bulb? 100-watt light bulbs are intrinsically brighter, and so I can see them when they're farther away. 20-watt light bulbs are intrinsically dimmer, and so if I put them far away, I won't be able to see them at all. He didn't know the answer to that question. So he made an assumption, okay? And the assumption he's made is he said, well, I don't know what the brightness of every star is, but all stars are kind of the same. So let me assume that they're all the same brightness, okay? And your job as a scientist is when you make assumptions like that, is to simply be honest that you've made the assumption. So the rest of us listening to your story, the way you're listening to the story that I'm telling you right now, can decide, okay, that's not the right thing to do because he doesn't really know, but I can carry that along with me and decide how much of this story he's telling me about his map of the Milky Way that I believe, okay? So in order to demonstrate this, I went out in my backyard with 2 flashlights, and those 2 flashlights are the same brightness, and I've put them at exactly the same distance away when I took this picture. So in the picture, they look roughly the same size because photography, okay? Now, the reason this was important for Herschel is that if you move one of the stars away, farther away, it will get dimmer. And so in the context of the image you're looking at here, the star that's near, labeled as near, didn't move at all. It looks roughly the same size as it did when I started, but the one that I carried farther away looks dimmer. If I do the exact opposite and I move what used to be the near flashlight farther away, it looks smaller in the picture, and so it looks dimmer. So this is the foundation of what Herschel did, is he assumed every star was the same brightness, and if he looked at it in its telescope and it was dim, it was far away. And if he looked at it in his telescope and it was bright, he said it was close. So in this way, he could just measure the brightness of the stars in his telescope and map how far away they are whenever he looked out through the Milky Way galaxy. To do this experiment, he used a piece of technology. So since Galileo's day, the telescopes got bigger. That is still true today. Telescopes get bigger and bigger with time. This telescope is called the 40-foot telescope. It's a very famous one that Herschel built. You can see they didn't have the kind of technology, particularly metallurgy, that we have today to build telescopes. So they have these enormous contraptions to lift and spin the telescope to allow it to point anywhere in the sky. They used to describe telescopes there by how long they are. So that's the 40-foot number. But in modern parlance, what we do is we describe telescopes in terms of how big the mirror is. If I put a ruler across the center of the mirror, what's its diameter? So in modern language, this would have been called a 48-inch telescope. So the way this works is a person stands in that little cage up there at the top edge of the telescope. They look in a little eyepiece that's mounted on the rim of the telescope, and they call the results down to a person on the ground who's recording what they see in a notebook. Okay, so what he did was he measured, he counted the stars in every direction in the sky, in 683 different directions in the sky through his telescope. And then he used all of those descriptions of how many stars are close, how many are midway, how many farther away, to build the very first map of the Milky Way galaxy. Okay, and this is what that map looks like. This is, whoops, I went the wrong direction and it's not going. Looks like I'm going through this again. I don't know how I went backwards. I probably hit the wrong key. This was the very first map of the Milky Way ever drawn. And what Herschel wrote about it is that the Milky Way is a very extensive branching compound congeries, that clustering word again, of many millions of stars. Okay, so we've gone up from many thousands to many millions of stars, which most probably owes its origin to many remarkably large, as well as pretty closely scattered small stars that may have drawn together the rest. And I've highlighted the yellow part down there because this fundamentally marks one of the most important transitions in astronomy, the one that leads to the work that I personally do today. This map that Herschel made was made just about 100 years after Newton first wrote down the mathematical description for how gravity works, what today we call the universal law of gravitation. And you can see how that idea percolates itself into the scientific community and is adopted and used to explain what we see. Herschel here is exploiting that knowledge that gravity holds the universe together to put forth the idea that the shape of the Milky Way here in this large flat disk is because the gravity of the Milky Way is binding itself together. And this is one of the first places you ever see that written down. Those of you who are familiar with the Milky Way will recognize some structure here. In particular, this large dark band over here on the left. That is the direction of Cygnus, which is directly overhead here in the Northern Hemisphere in the summer. It's an area where gas and dust blocks out the light of the stars behind it. It's called the Great Rift in Cygnus usually, and you can see it very clearly standing out in Herschel's map here. You'll notice there's an edge to his map. So he and Carolyn were the very first ones to recognize that the Milky Way was finite in extent, and indeed the number of stars drops off after a certain distance, okay? Now, you'll notice right here in the center, there is one star marked, and that is Herschel's assessment of where the sun is in the galaxy, very near to the center, okay? But that begs a question, right? We're formulating our story of our understanding of the Milky Way in terms of questions, is where is the sun in the galaxy, okay? And to answer that question, you have to solve the hardest problem in astronomy. Even today, the hardest problem in astronomy is measuring distances. Measuring distance is absolutely the most difficult thing you can imagine doing because the practical ways you learn to measure distances on Earth with rulers or by walking somewhere cannot be done in astronomy. We have to figure out how to measure distances solely by the information we can gather in a telescope. And so to take Herschel's sun, which was near the center of his map, and place it in the correct place in the galaxy would require a breakthrough in our ability to measure distances. Herschel did his map in 1785, and the breakthrough in measuring distances in astronomy wouldn't happen until 1908, okay? So in 1908, the puzzle was cracked. The riddle was broken by a woman at Harvard named Henrietta Swan-Leavitt. And when people ask me, what is the most fundamental and the most important discovery in astronomy? It's the discovery that Henrietta Swan-Leavitt made. Leavitt was the first person to figure out how to measure distances in the universe that are far larger than anything that had ever been attempted before. She developed what we call the first rung on the distance ladder. It's the foundation on which all other distance measures are built. It was discovered in data that she was studying from a nearby galaxy to the Milky Way called the Large Magellanic Cloud. And by observing a particular type of star that occurs throughout the entire universe. It's called the Cepheid variable, and it gets brighter and dimmer over time, naturally. Okay, so it's not quite as dramatic as Christmas lights, but you can imagine it's slowly getting brighter and then slowly getting dimmer and slowly getting brighter and slowly getting dimmer. And Leavitt was the first person to look at these stars and figure out that they could be used to measure distances. So we call this today Leavitt's law. And basically the fundamental principle is that if you can see it in your telescope and measure the brightness, and you can time with your wristwatch how long it takes it to get bright and dim again, then you can turn those two numbers into a distance. Mathematically, those of you who are familiar with astronomy will know the mathematical relationship is called the Cepheid period luminosity relationship. It's the mathematical conversion between those two numbers. But Henrietta Swan Leavitt was the very first person ever to discover it. And astronomers instantly knew that she had solved the puzzle. And they immediately put it to use to answer this question about where the sun is in the Milky Way. Okay, so the person to do that was a gentleman named Harlow Shapley. So Shapley at that time was at the Mount Wilson Observatory, which was the preeminent observatory in the world. It's on Mount Wilson over what is today Pasadena in Southern California. And they had built the largest telescopes in the world. First, the 60-inch telescope, a little bit bigger than the one Carolyn and William Herschel were using, and then the 100-inch telescope. And the 100-inch telescope came online in 1919, a little bit shortly after this work that I'm telling you about right here. Shapley was interested in globular clusters. So this is an image of a famous globular cluster called NGC 6388. It's in the constellation Scorpius for those of you who go out and stare at the stars at night. The globular clusters are exactly that. They're balls, they're globs of hundreds of thousands of stars. They're very old stars. They've played a very important role in our understanding of the history and evolution of the universe. But the Milky Way has a whole bunch of these, about 150 of them, that orbit the Milky Way galaxy, always staying together in these balls, but orbiting the galaxy the same way a star might orbit the galaxy, or the same way a planet might orbit the sun. And so Shapley was studying these with telescopes, and he had the wherewithal to recognize that if he wanted to know where they are, measure their distances, he could use Leavitt's law to measure the distances to all the globular clusters in the Milky Way. And so he set about doing that. Okay, and what he did is he made a map. Now this map, for many of you, will be reminiscent of the kinds of graphs you learned to do when you were in math and science class in your education. It's an XY graph, just like you draw on a piece of graph paper. And so horizontally is the X distance and vertically is the Y distance. And so Shapley just plotted each of those green dots, which is one of the Milky Way's globular clusters, and their distance from the Earth, depending on which direction he was looking in the sky. Okay, and what you'll notice is that the sun, the yellow ball right there in the middle, is not near the center of all those globular clusters. The center of all those globular clusters is where the X is. Okay, and so Shapley immediately realized that this meant the sun was not at the center of the Milky Way. It's actually partway out from the center to the edge, the place where I showed you its location on that very first picture of the Milky Way. Okay, so this was the first realization that the sun wasn't at the center, because we know that the Milky Way's gravity is the most important thing in our area of the universe. And so the globular clusters pay attention to it, not to the sun. So this, going back to our original image, is how we discovered where the sun actually was, but it also allowed us to measure the size of the Milky Way. So if you were to travel from one side of the Milky Way all to the other, it is 100,000 light years across. Now, those of you who don't study astronomy may not have heard that term before. A light year is not a measure of time, it's a measure of distance. It's the distance light travels in 1 year. So it's the maximum distance anything can get in the universe in 1 year, because nothing can travel faster than the speed of light. So no matter how fast you can go, it would take you 100,000 years to travel from one side of the Milky Way to the other. Now, you and I, we drive around in cars and fly around in airplanes. We're not used to thinking about things in terms of light years. So you might feel compelled to convert that to, in the United States, miles. That is 588 quadrillion miles. That's 588 with 15 zeros after it. So this is why we use light years, because you and I, even though we know what miles are, we still don't know what a quadrillion miles is. It's far outside any of our everyday human experience. And this is the great difficulty that we always have with astronomy, is that eventually, as we push the boundaries of our knowledge, eventually, as we try and discover more about our place in the universe, it becomes so mind-bogglingly large that even though we can write down the numbers, that we can make the measurements, it's hard for our human brains to comprehend. The sun and the planets around the sun are just one small, tiny corner of this enormous galaxy that we live in. Okay, but we keep pushing farther, right? We never let that stop us, because our curiosity is insatiable. And so once you ask yourself and have figured out what the nature of the Milky Way is, you may ask yourself, well, I wonder if the Milky Way is the only galaxy. Is the Milky Way the only place in the universe, or are there many other galaxies as well far outside the Milky Way? That's a completely natural question, but in fact, it's one that completely vexed astronomers for almost a century, okay? And you can understand why. So in the olden days, back when Herschel was doing things with his telescope, you can see what things looked like in telescopes. So I've shown you two images here. On the left is actually another galaxy. It's called Centaurus A. It's visible in the southern parts of the United States and in the southern hemisphere in the constellation Centaurus. It looks like a fuzzy white blob with a dark lane through the middle of it. Okay, that dark lane is not unlike the Great Rift in Cygnus that we talked about a little while ago. On the right, also visible in the southern sky, and even from here in the mid-latitudes of North America during the summer, this is called the Trifid Nebula. It is a nebula, but you can see it looks like a dim, fuzzy white blob with dark lanes through it, which again are also dust blocking the light from the nebula behind it. So these things look very similar. And when you look at these things in a telescope, you can't tell that there's any difference between these. Our job as astronomers is to discover everything we possibly can about these two things to tell whether or not they're the same kind of thing or whether or not they're a different kind of thing. Okay, but we didn't know in the olden days. And so we resorted to calling all such fuzzy objects nebulae, which is Latin for cloud, because they kind of look like clouds. Okay, so that was the policy for a long, long time. But all of that was turned on its head in 1845, when, continually pushing technology to its limit, a gigantic telescope was built. So this telescope was built in Ireland. It's called the Leviathan of Parsonstown. It was so large, it had to be supported by a castle wall, which you can see there. It couldn't spin the way Herschel's telescope could. It could only be dragged from the horizontal up to the vertical and back down again. And so you basically had to point it in the sky and let the night sky drift by and see what you could see. Okay, so this was built by William Parsons. And in 1845, so it's 72 inches in diameter. You can see a person standing there. So that's a 6-foot diameter telescope mirror. He was the very first person to look at one of the nebulae and discover that it had interesting spiral-looking structure. And for reasons that I still don't understand, this is part of my history learning that I'm still trying to delve into, is this inspired him immediately to deduce that the spiral nebula he was looking at was what he called an island universe. This is code from the olden days of what you and I today call another galaxy. So let me show you his sketch. So this is his sketch from 1872 of a galaxy today that we call the Whirlpool Galaxy. It was called the Whirlpool Nebula. Okay, so this is M51. It has a very bright center. That's the black blotch there on the left. It has these very graceful spiral arms, which are reminiscent of the pictures of the Milky Way I've been showing you. And you'll notice there's another blotch over there to the right that is connected by a bridge of stars we now know to the much larger galaxy. So in fact, that's a smaller galaxy that is slowly being consumed by the larger galaxy. But Parsons saw this, and there was nothing more detailed about this image, about what he could see in his telescope, compared to those fuzzy images I just showed you a minute ago, other than it has spiral arms. Okay, it's still just a fuzzy cloud. But nevertheless, he called this thing an island universe, and it set off a 50-year debate among astronomers about whether or not the Milky Way was the entire universe, or whether or not there were other island universes, other galaxies far outside the boundaries of the Milky Way. As I said, that occupied astronomers for nearly 50 years. The reason that the question was not easily resolved is because this kind of measurement, trying to get better data, is really hard. But it was famously put together in a scientific meeting that was held in 1920 at the Smithsonian Institution. It was during the day. They had a normal scientific meeting. Those of you who are scientists in the audience will recognize this meeting as being just like any meeting that you and I might go to and give our scientific talks, where people came and presented their observations and their opinions about the great debate. And in the evening, they had a public lecture, just like the one you and I are having, where these two gentlemen took the stage and summarized for the people present at the Smithsonian Institution what the arguments were for and against the Milky Way being the only galaxy in the universe, or the Milky Way being one of many galaxies in the universe. On the side of the Milky Way is the entire universe was our friend Harlow Shapley. Shapley was the director of Mount Wilson Observatory, so he's a very prominent leader in the astronomy community, and he very firmly believed that the Milky Way was the only galaxy in the universe. It was the whole universe. And that belief was founded on his own personal experience trying to measure the Milky Way and these mind-bogglingly large numbers that you and I talked about. His colleague, Heber Curtis, was the director of the Allegheny Observatory in Pittsburgh. So the Allegheny Observatory is not there anymore, but it was a prominent observatory. And Curtis was on the side of the Milky Way as just one of many other galaxies in the universe. And so they presented all the scientific arguments, trying to spin them into understanding that the public presence could understand. And so this is this meeting, this public talk, is often called the Great Debate or the Shapley-Curtis debate. But fundamentally, the question couldn't be answered. The Great Debate meeting at the Smithsonian Institution resolved nothing because our data just wasn't good enough. So what data do you need in order to resolve this question? The data you need is you need to solve the hardest problem in astronomy. You have to measure the distances to one of the spiral nebulae. That's the only way this could easily be resolved. But fortunately, Leavitt's law gives us a way to do that. And just 4 short years after the Great Debate, this gentleman, Edwin Hubble, using this telescope, the 100-inch telescope on Mount Wilson, used Leavitt's law to resolve the debate. He was studying what was then called the Andromeda Nebula. It is known today to be the closest big galaxy to the Milky Way that's similar to the Milky Way. It is actually visible to your naked eye. So if you go out and you look to kind of your northeast sky right now, you can see the W shape of the constellation Cassiopeia. And if you're away from the city lights, you can see this with your naked eye, but a pair of binoculars will certainly sweep it up and you can see it in binoculars. Okay, so this will look like an elongated fuzzy blob in binoculars. It will look like an elongated fuzzy blob in telescopes. Okay, but if you have at your disposal a big telescope, a 100-inch telescope like Hubble had at Mount Wilson, you can try to resolve things in the nebula, in the Andromeda Nebula, that will let you measure the distance. Okay, and so I direct your, this is his plate taken on the 6th of October, 1923. Okay, and I'll direct your attention up there to the upper right corner. You'll see those 2 lines, and probably on your computer monitor you can't see, but there's a star right between those 2 lines. And it was originally marked by the letter N. So that was code for something in astronomy that we call novae. So novae are explosive events on the surfaces of stars that make them very bright for a little while, and then they get dim again. Okay, and novae happen all the time, and there had been a lot of work done on novae because it was one of the arguments being used to try and sway the great debate one way or the other. But you'll notice sometime later, Hubble had crossed out N and written var next to it. And that var is for variable star, a Cepheid variable to which he could apply Leavitt's law and successfully in 1924 measure the distance to the Andromeda Nebula, which we now know is the Andromeda Galaxy, because the distance that he measured was over 1 million light years, well outside the boundaries of the 100,000 light years that we had measured the Milky Way to be. Now that instantly, this is the remarkable thing about what technology does to astronomy. It happens all the time to us. We are confused, we've taken all kinds of data, we've done the best we can, but a single measurement can be powerful enough to completely transform the way we think about the universe. And this is an example of that. You were able to instantly just shatter the belief that the universe could only be 100,000 light years across and suddenly make it be not just 10 times larger, but the fact that there are galaxies even farther away than the Milky Way, than Andromeda, tens of thousands of times larger. This discovery made the modern universe that we know of today. Okay, and it's a completely separate talk, but Hubble spent the next 5 years doing this measurement on other galaxies, and ultimately with his colleagues Vestal Slipher and Milton Humason led to the discovery of the expansion of the universe. Okay, so fundamentally it changed the nature of astronomy. So this is kind of where we were 100 years or so ago. Around the time my grandparents were born, we had just discovered that the Milky Way was big. We had just discovered where we were in the Milky Way, and we had just discovered that there were other galaxies beside the Milky Way. And in the ensuing 100 years, we have endeavored to map out the Milky Way in more detail, to discover where all the stars came from and how old they are, what their compositions are, how the Milky Way has changed over time. The science of astronomy is dominated, is consumed by studies of all the things that now fill the Milky Way. But all of them fall back to these few fundamental discoveries that we made early on. So let me just take my last few minutes here to tell you about the work we do in CIERA on the Milky Way. Now, many of our groups in CIERA work on the Milky Way with different aspects of it, but I'm just going to focus on what my group does. Science is a collaborative endeavor. Vicki told you that at the beginning. We very seldom work at our desks all by ourselves anymore. So we have big teams of people who work with us. My faculty colleagues that I work most closely with are listed across the top there. Vicki is here at Northwestern with me, but my other colleagues are at other institutions around the country. And then on the bottom are all of my current stable of students who work with me. And all of them are working on different aspects of the Milky Way and the sorts of things that we think about, including my cat there, who's CIERA with an S, who also works with me when I'm working here at home all the time. What we do is we study the galaxy not with telescopes, but with gravitational telescopes. We do what's called gravitational wave astronomy. Some of you may have heard of this in the context of a ground-based observatory called LIGO, which has made very important discoveries in the transformative discoveries in the last 5 years or so. But I'm working on a mission that's a future telescope, one we're going to build in space called LISA, the Laser Interferometer Space Antenna. It will be comprised of 3 individual satellites that shine laser beams back and forth between them. And by measuring those laser beams, we can detect gravitational waves propagating through the universe. And what my group in particular focuses on is gravitational waves that come from our own Milky Way galaxy. Okay, so what we do is we theoretically simulate what the gravitational wave signal from the Milky Way galaxy looks like. So let me tell you about that. Oh, this is what LISA looks like built out of Lego. So what we do is we simulate computer galaxies, and then we use those to simulate what LISA will see when it finally flies. We use this to prepare ourselves for how to work with the data and how to interpret the data so that we can understand what the Milky Way is all about. Okay, and so the way we do that is we have a few simple rules that tell us how stars are born, how they live their lives, and how they die. And we take those simple rules and we tell the computer, make stars according to these rules, and it creates a galaxy for us. And then we take that galaxy and we push it through our LISA simulation. Okay, so to explain how that works, let me imagine us simulating the audience listening to me today. So I did this for 80 people, but I see we have 345 people on the call. So this will be like my next slide. But if I were to just take a subset of people in the lecture and ask, what is your age distribution? I could count you up and I would know that for every 80 people I take out of the audience, 12.5% of you will be old folks, 25% of you will be middle-aged folks, 31.25 will be adults, 18.75 will be college kids, and 12.5% of you will be little kids, okay? And I know that those numbers will be true no matter what 80 people I take from the audience. Okay, so this is what the nature of statistics is that if you take a random sample, you assume the random group that you pull out of the audience is no different really than the next random group that you pull out, provided the number of people you're talking about is large enough, right? It won't work if I only pick 7 people, but it'll work if I pick 100 people. So we have rules like this that tell us about the stars that we see in the Milky Way. And so if I were to simulate an audience, I can do this by simulating many more people up to the number of people that we see in the audience, or maybe larger. And all of these lines represent simulations of audiences that accurately reflect the age of the people in the audience I start with. Even though there's 368, 737, 941, 577, 377 people in each of those groups, the percentages are all approximately the same as the percentages I measured when I measured the first time. And so this is what we do in our group. We figured out what those little percentages are about all the stars in the Milky Way. And now we simulate the galaxy over and over and over again to discover what's in it and what's making gravitational waves. How many white dwarfs are there? How many dead stars are there? How many black holes are there? And then we study all of that information to understand how we might learn more about the Milky Way. So just like there's rules for peoples, there's rules for making stars. We ask how big is the star when it's born. We ask how many big stars versus little stars are born. We ask, is the star born with a partner in what astronomers call a binary? We ask, are they born close together or far apart? We ask, where were they born and how long do they live and die and what are they made of? We have this long list of rules and we have them in the computer and it just makes stars for us. And the outcome of that is models about what the Milky Way might be like. Now, we don't know everything there is to know about the Milky Way. And so some of our models show a Milky Way like you see on the left. You'll notice that galaxy is kind of thin. Some of our models show a Milky Way like the one that you see on the right. That one's a bit bulgier in the middle. Okay, and that's related to the fact that we don't understand exactly what the shape of the Milky Way is because we've never been able to look at it from the outside. But this simulation shows us that an observatory, a telescope like LISA, may be able to tell us what the difference in the shape of the Milky Way is. The other thing we do is we ask, how might LISA work together with other telescopes? So this is zooming out from the sun in one of our simulations. And what you'll see is every little dot that's appearing is a star that LISA will be able to see in gravitational waves. And if you can see the color on your monitor, you'll see some of those stars are purple and some of those stars are red. The red stars we will only be able to see with LISA in gravitational waves. But the purple stars we can see with LISA and with a traditional telescope. And that gives us an extreme advantage in terms of measuring the properties of those stars and understanding what's happened to them over the course of their lives. Okay, and so this is the sort of thing that we do. We simulate this so that we can prepare the kinds of instruments and the kinds of observations that we'll have to have when LISA flies in about 10 years. Okay, so that is all I'm going to say. I'll leave you with a few thoughts here, which is that our understanding of the Milky Way changes with our ability to observe. The application of technology to the understanding of the universe is one of the key features that drives modern science. In order to understand our place in the universe better, we have to improve our ability to observe, our ability to make measurements. And in astronomy, that's particularly hard because nothing is here close to us. Everything is far out there. So we build bigger telescopes. We build different telescopes like LISA. Our understanding is always changing, and what that does is that changes our ability to ask questions. Fundamentally, in the distant past, we used to only be able to ask, where are the stars and in what direction? We didn't have a way of mapping out the shape of the Milky Way until we could measure distances accurately. Today, we ask different questions because we have different technology. We can ask, what is the galaxy made of? We can ask, how is the galaxy changing over time? We can ask, where are stars being born and where are stars dying? Right? Our ability to observe changes the questions we can ask, okay? And then lastly, I'd just like to remind people is that, 100 years ago, when my grandmother was born, we had just discovered that the Milky Way was a galaxy at all. And today we know all the things that you hear about and you read about when you read about astronomy in the news and in textbooks. And so if I were to imagine that what you and I know about the Milky Way today is a limited set of knowledge equivalent to what they knew when my grandmother was born, the kids in the audience today will know infinitely more about the Milky Way in 100 years when we have applied all of this technology over and over again to discover in much deeper ways than we can today what our place in the universe actually is. Okay? So I always like to leave you with a few things to go read and study on your own. There's a few books here. The top two, The Insider's Guide to the Milky Way and The Milky Way Owner's Workshop, are really guides about the physical structure and how we came to understand the physical structure of the Milky Way. They're both very good. They have a little bit of history in them and a little bit about technology and what astronomers are still wondering about the Milky Way. The Glass Universe there by Deva Sobel is an excellent book about the Harvard computers, the group of women who were at the heart of a lot of the astronomical discoveries at the turn of the 20th century, including Henrietta Swan-Leavitt. She had many other really very talented women who worked with her and were also responsible for many of the other discoveries. And this book is a particularly excellent recounting of the work that they did. There's the link there at the end to Herschel's mapping paper, as well as the link to the CIERA website, where you can see all sorts of stuff, including lectures we've participated in, our simulations of our galaxies, and work that our group's doing, and so on. So you can certainly spend some time there and further your education in astronomy if it suits you. So with that, I'm going to say thank you for your time and attention. Thank you so much for joining us and taking time out of your evening today. And I'm going to let Vicki go ahead and start in on the Q&A.
Thank you, Shane. You're only getting a clap from me.
That's okay. That's the way these go.
In these days. So thank you for the talk. It's always wonderful for me to hear you and see you give public lectures. Now, we're going to transition to answering questions. We have actually a lot of questions right now. So Shane, you have to be succinct and quick in your answers, but also clear. So that's your challenge. So we'll begin with some questions, and please, you can keep them coming. So here's the first question. From Larry Majors, is the Milky Way being pulled towards another galaxy? If so, what will be the ultimate outcome for the galaxy, for our galaxy, and for the sun?
Yeah, so that's a great question. It's actually one we know the answer to, and it's a question that we've actually studied on computers. So right now, the Milky Way and the Andromeda Galaxy are falling towards each other at about 125 kilometers per second. Okay, so you can figure it out. We've gotten much closer together in just the time that you've been listening to this talk. In about 3 billion years, the two galaxies will come together and collide. And so when that happens, future people on Earth will look up in the night sky and not just see one Milky Way, but they'll see what you and I would call two Milky Ways, basically crisscross across each other in the sky. And one of those will be the disk of our own galaxy, and the other will be the disk of the Andromeda Galaxy coming towards us. The ultimate outcome of that is something that we study in astronomy. We believe that when galaxies collide, they merge, that this disrupts the spiral structure of galaxies, and they settle down into something called an elliptical galaxy, which is kind of shaped like an American football or a rugby ball. It's kind of oblong and ball shaped. And those elliptical galaxies are the result, we think, of galactic mergers. And so that will ultimately be the fate of the Milky Way and Andromeda. Now, in numerical simulations, if we look at what happens to the sun's orbit, we think, will be disrupted by this. It will be very near the end of the sun's life, so the Earth and the planets will be gone, but the sun's orbit will turn into what we call a plunging orbit. So the sun will basically fall straight down through the middle of the galaxy, out the other side, and then back and forth again like a big yo-yo. So that's what ultimately will happen to the sun.
Okay, next question from a 6-year-old, Lynn, his name is Max, Lynn Gilbertson's son. He's a huge fan of comparing relative sizes to all things in the universe. He's wondering if you have a favorite galaxy or a favorite black hole or a star. Max's favorite black hole is the Bootes void, and favorite star is VY Canis Majoris.
Okay. Yeah, so I do have favorites of all of those things, because one of the things that for me is true is I'm a professional astronomer, but I'm also an amateur astronomer, which means I go out in my backyard and look at things with my telescope. So one of my favorite galaxies to look at with my telescope is a galaxy called NGC 891. It's a galaxy over near Andromeda that's completely edge on. So when you look at it, it just looks like a toothpick in the sky. It's really cool. And if your telescope's big enough, you can see it has one of those dark lanes right through the center, which I really enjoy being able to see in my telescope. My favorite star is actually a star in the constellation Cygnus, which is called Albireo. It's a double star. There's basically two stars in the same line of sight when you look at it in the sky. And I like them because in the telescope, they look different colors. One of them looks blue and one of them looks yellow. And then my favorite black hole actually lives at the center of the Milky Way. It's called Sagittarius A star. It's the biggest black hole closest to the Earth. And if you've been paying attention to the news, there was a very big prize given in physics just a couple of weeks ago to a colleague of ours, Andrea Ghez at UCLA, for her work studying that black hole at the center of the galaxy. So that's my favorite black hole.
That's fantastic, because there were a few questions about what's in the center of our galaxy and what's going on with Sagittarius A star. So you covered a few. So Natalia Whiteley's daughter wants to know if all the systems we call galaxies could be smaller components of a much larger galaxy of others of the same type in an unending infinite universe.
Yeah, so that's a really great question. And the answer is yes. Galaxies are formed of lots of stars living together in the same place. But one of the things that we've discovered, because we have telescopes that we've looked at all over the sky and mapped out where the galaxies are, we've discovered that galaxies cluster together in little neighborhoods. So we call these clusters, and then there are much bigger groups that we call superclusters. And so they apparently have formed together. We think it has something to do with the dark matter in the universe, which is this exotic substance that fills the universe and affects everything with its gravity. We don't know much about it, but the galaxies cluster along the dark matter pattern in the sky. And so even with a telescope in your backyard, you can see some of these clusters. The most famous one, the closest one to us, is called the Virgo cluster. It's in the direction of the constellation Virgo. And there are about 2,000 galaxies that live right there together in the Virgo cluster.
Great. Another question from Myra Littman. She's a high school student. Why do we think the galaxy is formed into a spiral if we have never seen it?
Yeah, so that's a really hard question to answer, because it's related to something I told you earlier, which is that we don't always know the answer to questions because we simply can't observe the things happening. And what you said in your question is really important. The time scale over which things happen in the universe is enormous compared to a human lifetime. We can never, ever observe a galaxy from the moment it forms to the moment it becomes a spiral galaxy, to the moment that it collides with some other galaxy and becomes an elliptical. That's just too long compared to how long humans live. So we do two things. We look at galaxies in all their different stages of life, and we try and put them in an order that makes a story. So galaxies that are just forming versus galaxies that are forming spiral arms versus galaxies in the middle of collisions and galaxies that have become ellipticals. And we look at the properties and we say, okay, we put them in this order. Do the properties make sense? Do all the things that we can observe about the galaxies make sense when we have them put together in this order that we think represents their life? We do the same thing with stars. With galaxies, it's hard because seeing galaxies when they're young means we have to see really, really far away in the universe. So the other thing we do, and we do this kind of work in CIERA, is we simulate them on computers. And so when we simulate them on computers, we simulate their early lives, but we let them run forward in time to the modern day. And then we ask, do those modern galaxies look like the ones we can see in telescopes? And if they do, then we hope, we believe, that the way they were when they were young in our computer simulations is probably close to correct. So that's the way we do it. And it's a very difficult way to do science because you're completely constrained by your inability to see the galaxy evolve over time.
Okay, here's a couple of combined questions about dark matter. One, if you can quickly explain, how do we know dark matter exists? And second, can we ever determine the ratio of dark matter in the Milky Way?
Okay, those are both really good questions. So there are lots of different ways that astronomers recognize that dark matter is present in the universe. The one that's involving galaxies was originally noted by an astronomer named Fritz Zwicky in about 1935 or so, but it was really made prominent by an astronomer named Vera Rubin. And so what Vera Rubin did with her colleagues in the 1960s, I guess, they would look at galaxies. And one of the things astronomers can do is they can measure how fast the galaxy is rotating as you go from the center out to the edge of the galaxy. Okay, so that rotation is done by looking at the light from the stars and the gas and measuring the rainbow lines that we see in the light. And there's a way to turn that into speed. What we expect, if we just look at the galaxy and assume all the gravity is caused by the stars that you can see, is that as you get farther out towards the edge, the galaxy should start to spin slower. And what Vera Rubin and her colleagues discovered is that galaxies are rotating much faster on the outside edge than expected. And that faster rotation can only be explained if the gravity is stronger. And since gravity is created by massive things, if it's more gravity than expected, there must be matter that we can't see. And so Fritz Zwicky originally called this missing matter, but Rubin and her colleagues call it dark matter, because no matter how hard we look, we never see any light coming from that matter. So this is probably the strongest evidence there is for dark matter, is looking at these rotation curves, as we call them, for galaxies. Now, the Milky Way, we know, I would say exactly how much dark matter there is because we've measured the speed that the Milky Way is rotating. And this is something that some of my students and I have been working on, is trying to understand how the rotation of the Milky Way tells you about the dark matter. And then we're asking the question, can we measure the dark matter with gravitational waves? And we hope to have an answer to that soon. We'll see.
So a question from Amy Paulsen, Michelle's daughter. She's a high school student. Can we see with a telescope any galaxies that are currently merging? How can we tell that this is what's happening?
Yeah, so that's a great question. So if I had prepared the slide, I could have shown, oh, I do have a slide. Nope, I don't have a slide, sorry. So there are many galaxies that we can see that are in the middle of collision. And so the most famous one, if you go Google the image, they're called the antennae galaxy. Okay, so basically there's two blobs that are basically the cores of the galaxies. They're almost exactly on top of each other. And what it looks like they have, the reason they have the name is there's these very long tails of stars that basically look like unwound spiral arms. Okay, and so what's happening is we can simulate this on the computer, right? Is when the galaxies get close together, the bulge stays very intact because the gravity is strong enough to do that. But the stars in the arms kind of get left behind. We call that tidal stripping. And so these very long tails are called tidal tails. And so the antenna galaxy, which you can see with the backyard telescope, is probably one of the prime examples of these galaxies that are in the middle of merger. And we see many galaxies like this. There are whole catalogs of galaxies that look like they're in the middle of merger that you can look up.
How will multi-messenger astronomy integrate with LISA?
Yeah, so there's a couple of different ways. That's a good question. So we're trying to understand this question right now. This occupies the minds of lots of astronomers. So in my group, the thing that we're interested in is the stars in the Milky Way that we can see with telescopes and LISA at the same time. Mostly that corresponds to a group of dead stars called the white dwarf binaries. They are stars that when they were in the middle of their lives were not unlike the sun. They were kind of ordinary yellowish stars, but when they die, they shrink down to become something about the size of the Earth. And so they're dim, but they are very hot. And so they can still be seen with telescopes. And so one of the things that we can do, that we hope to be able to do, is to observe them in telescopes, which using the light, we can tell what's their composition and how strong is the gravity at the surface and what's the shape of the orbit. There's all kinds of information like that. And then with gravitational waves, we can tell you things like how is the orbit tipped to our line of sight and what is the relative masses of the two stars and has one of the stars distorted the other one. So the combination of both the light and the gravitational waves will tell us something about the state that the dead stars, the skeletons, have found themselves in. And so we often liken this to, the way an archaeologist would study the ruins of Pompeii. We can learn about the people who lived in Pompeii before the volcanic eruption by studying what was left behind when their skeletons were buried. And this is basically what we're doing with the Milky Way. We're going to study the stars, the skeletal stars, and try and understand what the history of the galaxy before those stars was born. But we need both. We can do more if we have both telescopes and gravitational waves. Okay. They'll also study big black holes with gravitational waves and telescopes at the same time and a variety of other phenomena. But there's a lot more uncertainty in those cases than there are with the white dwarfs. The white dwarfs, we already know where lots of them are and we can see them in telescopes, which is why we're interested in that.
Quick question. A lot of people are asking, what's the effect of the supermassive black hole in the center of our galaxy? What's that its effect to the rest of the galaxy? Could it ever swallow our galaxy?
Okay, so that's a good question. This is one that we all ask all the time, because when we're taught about black holes, we're taught that black holes are little hoovers that run around scooping up everything in the universe because their gravity's so strong. And the kind of fundamental definition of black holes is their gravity is so strong you can't get away from them. That's why we have that idea. But when you think about the galaxy, the thing to remember is that the black hole at the center of the galaxy is only 1 million times bigger than our sun in terms of its mass. If I could stick it on a scale and measure its mass, it would be 1 million times more massive than the sun, which means its gravity is about 1 million times stronger than the gravity of the sun. But the sun, remember, lives way out here, okay, out in one of these spiral arms. And so the total gravity that the sun sees is really the gravity from the galaxy, which is the gravity of 400 billion individual stars. So the gravity of all the stars is much more important than just the gravity of that black hole that's down near the center. The stars that care about the black hole are the ones that are down close to the black hole. As you get closer and closer and closer, the only gravity that matters is what you see in the center. And since all of the stars are in the outside of the galaxy and you're down near the center, then the black hole's gravity means a lot more to you. And the Nobel Prize that was recently given was for studying stars who are in orbits around that black hole, and their fate is intimately entwined to the fact that they will eventually fall into that black hole.
Okay, so we're gonna close at 8:15, and there is an
Okay.
extended duration because we still have hundreds of people attending, and we have dozens of questions. So we're gonna
Okay.
squeeze as many as we can. A
We'll take a
few
few more.
questions about LISA.
Okay.
What's the timeline? Who is building it? Will the data be available to all the countries? Go ahead.
Yeah, so those are good questions. They occupy a lot of time in scientists' minds. So the timeline for LISA is sometime after 2030. 2030 to 2034 is the timeline right now, which most of us are expecting. It's being built by the European Space Agency, which is a conglomeration of countries that do space missions together in the European Union. And then also NASA is what we call a junior partner. So we're a major player in that effort. So here in the United States, we have people at universities all over the country who work on LISA, including here at Northwestern. My group works on LISA. And then as well as the NASA centers. So there's folks at Marshall Space Flight Center, folks at Goddard, folks at JPL who also work. And so we do both science, the sorts of stuff that I've been talking to you about, as well as build hardware. So we're building telescopes and we're working on lasers and thrusters and those sorts of things. So it's, as with all big science in the modern era, it's very difficult to do big science on your own. It takes real, true international efforts. And LISA, I think, is certainly a good example of that. So that will happen, yeah, in about a decade, maybe, you know how building space missions is, probably 10 to 20 years is when you should expect it. The data should be public. This is the way things are going because people like me and you pay taxes, and that pays for science, and that means we own the data. So the data will be out there for everyone when
Actually, this is a good segue to another question. Are there any practical applications we can find useful in daily life from understanding the Milky Way? I would expand it maybe to, you know, the science you talked about.
Yeah, so that's a good question. And this is the question that I think all of us as scientists always get. And so let me kind of say two things. So the first thing is that the kind of science that we're doing right now is what we call fundamental science. It's the very foundations of what scientific knowledge is. It's at the very edge of what we understand. And so as a consequence of that, we don't really know how to take that knowledge and turn it into useful things that will improve your golf game or make your life in the kitchen easier or whatever, okay? Fundamental knowledge is about building the foundations of human understanding of the universe. But over time, as that knowledge becomes very comfortable for us, then we begin to use it to do other things. And so the primary way it begins to filter back is through the technology itself. The technology that we built the observatories around is often the first thing that comes back to the public for the greater good of humanity. And so examples of that are the distribution of our data is so large and so complicated that it directly influences the kind of data transfer technology and the way that we spread information around the world. So famously, the World Wide Web was developed by our particle physics colleagues so they could share particle physics data. In astronomy, one of the most famous examples, those of you who are my age will remember that when the Hubble Space Telescope launched, its mirror was slightly deformed. And so astronomers had to work on computer programs that would take the images and correct them so you could make really crisp images like the image you see behind me rather than the kind of fuzzy ones that we got back when we first launched it. Today, that imaging technology has made it into medical imaging and is used for things like mammograms. And so it has filtered back into common usage precisely because we've had decades to figure out ways to be clever and use this for other purposes. So at the edge where my group works, right, the understanding of what this will transform our daily lives about is a question for the future. But I have every confidence, based on every scientific experiment that's ever been done, that 10 years or 20 years after the mission, that the technology will transform itself into something new that will change the way you and I lead our everyday lives.
I cannot resist. Last question. from Max.
Okay, last question, Vicky.
The 6-year-old. It's close to our heart, Shane. Could two black holes ever collide and create a massive explosion, or would something else happen?
Yeah, so that's a great question. So yes, big black holes collide, and we have seen them collide using these gravitational wave telescopes that I've been telling you about. In fact, LIGO, which I also work on and Vicky works on, was the very first gravitational wave telescope to make that discovery about 5 years ago. So right around I think you said you were 6, so it's right around the time you were born. So to call it an explosion, though, is interesting because it did create the biggest energy that astronomers have ever measured in the universe. Okay, but it's not the kind of explosion you and I think about when we go out and we watch firecrackers or blow up a stick of dynamite or something, right? It was an explosion in the physics and astronomy sense, which is a lot of energy was released, and there was more energy released in that black hole collision than any other explosion astronomers have ever seen. So the answer to your question is yes, absolutely, but maybe not in the sense that you originally thought when you asked the question.
Excellent. So I am afraid we will end here. We thank you everyone for coming. I hope you all enjoyed this glimpse into the Milky Way tonight and all the other topics Shane covered through the questions. Thank you for being with us online for this event, and please join us again. You can watch our social media or sign up for our emails to stay in touch about future events. And there was a question about when will the video be posted, the recording, and usually that takes about a week because there is some editing to be done, etc. So that will usually takes about a week, not full time, but people are busy with other things as well. So thank you, Shane, and thank you again, and good night.
Good night, everybody.